Okay, hello everybody who's viewing the FDM workshop. We're going to have two talks in this session from Michele Cicoli and Veronica Guidetti, and they're going to be telling us about fuzzy dark matter models in string theory. So Michele is going to go first, so take it away, Michele, and yeah, share your screen.
Yeah. Good. So can you see my screen?
Yeah.
Yeah. Okay. So let me start by thanking Dodi and all the other organizers of this Fuzzy Dark Matter workshop for the invitation to give this talk. So thank you very much. And so as Dodi said, this is going to be divided into two talks. The first one, which is a generic introduction to the properties of axioms coming from strings. And then the main thing is Veronica's talk. So she will talk after me and she will try to answer the question about how natural fuzzy dark matter is from the string theory point of view, starting from what I said. So here there are two, I guess you can see the arrow. So these are two, this is an old paper that I wrote with Dutzen and Ringwald, and this is a review on axiom properties, which is actually a contribution to the proceedings of a workshop. So you know this probably very well. Axioms have the strong CP problem. Axioms are nice because they solve the strong CP problem, where there is a U1 Pechequin symmetry which is anomalous and it gets spontaneously broken at an energy scale Fa that in the end would set the axiom decay constant. So the axiom is the pseudo-Goldstone boson associated with this U1 Pechequin, and it enjoys a continuous shift symmetry. What is important for the QCD axiom is the breaking of this symmetry down to discrete shift symmetry like QCD instantons, and then one generates depending on the model, but generate couplings in general to gluons, photons, fermions, and all of these are controlled by the axiom decay constant phi. The important thing is that the axiom develops a potential V, which fixes its vacuum expectation value to 0, so that the effective theta angle vanishes. And the axiom decay and the axiom mass is set by lambda QCD squared over the axiom decay constant. And from the phonological point of view, there is an allowed window for phi with a lower bound. It is roughly speaking around 10 to the 9 GeV from star cooling and direct searches. And there is an upper bound which is somehow less stringent, around 10 to 12 GeV, coming from dark matter overproduction. And I'm saying that this is less stringent because one can relax this bound. For example, if there is a late time dilution due to entropy injection, for example, from the decay of heavy particles, which is something that from the string theory point of view seems quite natural, or one can rely also on inflation and anthropics. Now, another very quick slide on axioms of phenomenology. The phenomenology is different depending on the fact that the axiom decay constant is smaller or larger than the Hubble scale h during inflation. So if Fa is below h, the axioms are heavy during inflation, and the U1 Pechequin symmetry is broken after inflation, so one has got no isocurvature fluctuations, but there is the generation of domain walls and axionic strings. On the other hand, when Fa is larger than h, the U1 Pechequin symmetry is broken during inflation, so the axioms are very light. So they develop isocurvature fluctuations during inflation, whose size is controlled by the Hubble constant. And the nice thing is that CMB observations like those from the Planck collaboration constrain the amount of isoculture perturbations quite well. And so you see that there is a combined bound which involves the axial decay constant and H. Well, H, for example, we know nowadays that cannot be larger than something of order 10 to the 14 GeV from the known observation of primordial gravity waves. Now, on top of applications to dark matter, actions are very interesting because they can be used for many other things. Probably this is not the main topic of this workshop, but let me just mention that they are interesting candidates for inflation because of their shift symmetry, but this pushes you towards quite large axial masses and decay constant. They can also be dark radiation. For example, if they are produced from the decay of heavy fields, in this case they are relativistic, and they contribute to the number of effective neutrinos, relaxing a bit the tension between Planck and the Hubble Space Telescope. They can behave as quintessence fields as well. And on top of that, axial-like particles can explain several astrophysical anomalies coming from the transparency of the universe for gamma rays, white dwarf cooling, the soft X-ray excess in galaxy clusters, the 3.5 kb line. And here it's nice because all these astrophysical hints point towards the same region where FA is intermediate, and the axons are very light. So after this very quick review, I think that from the point of view of a string theorist, the question is, what is the origin of this axion shift symmetry, which from the point of view of the effective field theory is just a symmetry that is postulated to be there. On top of that, question 2, one would like to understand what is the dynamics that breaks the D1 Pechet-Quinn spontaneously and set the scale of the axial decay constant. And once you are in a unique complete theory, there are many scales that get determined at the same time. So one would like to understand if there is some kind of correlation between the axial decay constant and other scales like the Planck scale, the string scale, the Kaluza-Klein scale, the grand unified, the scale of grand unification, or even the scale of supersymmetry breaking, where you give mass to the supersymmetric particles. So this is M salt. Another interesting question is what is the dynamics that breaks U1 Pechet-Quinn and explicitly and set the axion mass. And so the question is the axion mass generated by TCD instantons, as in the standard TCD picture, or by other purely string effects, which could be, for example, generalizations of electromagnetic fluxes in the extra dimensions, stringy instantons, worldsheet instantons, or any kind of contribution which could give a mass to the axion that is different from the one predicted by QCD. And on top of that, another question which I think is crucial for this workshop is, so on top of the QCD axion, you can get several particles which behave as the axion, so they are ALPs, axion-like particles, and what range of FA and MA they can have. So this is a very simple slide that motivates the axion origin from string theory. So from the naive quantum field theory point of view, a gauge field has got two self-couplings, G to the -2 and theta, which a priori are completely independent and unrelated. But if you start looking at these things from the point of view of a supersymmetric theory, you immediately see that the gauge coupling and the theta angle are related to each other because they are the real and the imaginary part of the same function, which is a holomorphic function f called the gauge kinetic function. And these can be either constant or field dependent. So here I'm taking the simplest example where this function is linear, where phi is a complex field with the real and the imaginary part, phi1 and phi2. And then one would have that G is set by phi1 and theta is set by phi2. So this simple argument tells you that any theory which has got supersymmetry and field-dependent couplings has axions. The main example of a theory which is also the best candidate we have for a consistent theory of quantum gravity is string theory, which needs supersymmetry for consistency, and on top of that has got no free parameter, which means that all these couplings will indeed be field dependent. Hence, one finds that in every string compactification, every gauge field has an associated axion, which means that due to the fact that there are many gauge fields in string theory, one expects also a plethora of axions in the low energy four-dimensional theory, which can arise from either closed strings or open strings. Now, these axions emerge always in fields, roughly speaking, like this phi, which are complex. They have an imaginary and real and an imaginary part, and these are called moduli. And actually, the phonological features of the axions, which could, for example, be the imaginary part, depend a lot on the dynamics of the real parts. So let me quickly mention what these moduli are to understand then the implications for axions. So string theory lives in 10D, 10 dimensions, and needs supersymmetry for consistency. One needs to compactify string theory down to 4 dimensions. So the 10D space-time is the Minkowski 4D times a 6-dimensional internal manifold. And one gets down to 4 dimensions by taking a low energy limit where you consider energies below the Kaluza-Klein scale, whose size is set by the volume of the extra dimensions. Now, the nice thing is that the geometrical and topological properties of the extra dimensions determine the properties of the 4-dimensional effective theory. And for example, the requirement of getting a supersymmetric n=1 effective theory, which is chiral, so that one can get the standard model out of a string compactification, tells you that this Y6D should be a Calabi-Yau manifold. Now, Calabi-Yau manifolds can be deformed in size and shape, remaining Calabi-Yau. And from the mathematical point of view, these deformations are called moduli, which from the 4-dimensional physics point of view correspond to new spin 0 particles with gravitational couplings to ordinary matter. And the axions will be part of this new complex field. And a nice feature is that of string compactification is that these moduli are massless at classical level, which means that they have a flat potential and their vacuum expectation value is unfixed. And this leads immediately to 2 problems. The first one is that given that they are gravitationally coupled to everything, they would mediate unobserved long-range field forces, which can be avoided only if they are heavier than 1 millielectron volt. And on top of that, as I said earlier, there is no free parameter in string theory, so all gauge couplings, Young-Mills couplings, Yukawa couplings, even the mass spectrum and the gauge group of the effective theory are functions of these moduli. So if you do not fix them, there is a lack of predictability of your effective theory. So the idea is to include in the effective theory also quantum corrections, which lift these flat directions and fix the moduli verbs by giving them a mass, which actually does not have just to be larger than 1 millielectron volt, but has to be larger than something of order 50 dB. So these guys have indeed to be very heavy, because otherwise they would create cosmological problems. For example, from knowing axion physics, you know that dark matter gets produced by the misalignment mechanism, The same thing is true for these moduli. They get misaligned during inflation. And so later on, when the Hubble constant becomes a quarter of their mass, they start oscillating around the minimum and very quickly come to dominate the energy density of the universe. So when they decay, they would dilute everything that has been produced before. And so one gets this very strict bound of 50 TeV by imposing that they do not decay before Big Bang photosynthesis. So that's an important bound also for action physics. Because we will see that they have some important consequences for actions. So this is a cartoon of the extra dimensions. So you see that there are these closed strings in the bulk, these moduli, and on top of that, you have also branes, which are space-time filling. And in the extra dimension, they can wrap some internal submanifold, or they can just be point-like in the extra dimension, so they can be located at singularities. And then you have open strings here that reproduce something that can look like the standard model, because these stacks of branes give rise to non-abelian gauge symmetries and current. So now let's see how actions can come from those strings. So as I said, you can have these UN gauge groups, which are realized on n dp branes, wrapping internal p-3 cycles. So if you go back, this could be an example. This is the 7 brane in type 2B string theory. So you have this is an 8-dimensional object. So 4 dimensions are space-time filling, and the other 4 are wrapping an internal submanifold, so an internal cycle. And when you look at the massless closed string spectrum, this contains anti-symmetric p-forms like the CP with gauge symmetry of this kind, CP that goes to CP plus d lambda p minus 1. And then if you look at the deep brane action, which has got schematically this form with DBI and Chern-Simons contributions, by expanding these actions, you find, skipping technical details, that from the DBI, you find the F mu term, and the G minus 2, so the gauge coupling, turns out to be just the volume of the internal manifold wrapped by this stack of branes, which I will call tau. By expanding the Chern-Simons action, instead, you find the axionic term F equals F, and then you find that the reduction of a p-3 form over the internal p-3 cycle would give you the axion theta. So this should be considered as a field. Theta is a function of x. So now you find that the gauge kinetic function, the one that I mentioned earlier, is indeed linear. So I was calling this field phi before, now I'm calling it t. Now t has got a real part tau, which is a modulus, and this is setting the gauge coupling. And then it's got an imaginary part theta, which couples to F equals F, and this is an axion. One can also see that actually this axionic, the standard axionic shift symmetry is inherited from the higher dimensional gauge symmetry. Good. Now, what are the phonological features of these closed string actions? Well, this depends on the way the shift symmetry is broken. So this can be broken at perturbative level. So if this is broken at perturbative level by background fluxes, so these are, as I said, fluxes of these p-forms which can get non-zero background values in the extra dimensions. So in general, they give a mass to these actions, which is according to the gravitino mass. And here is written in terms of the Planck mass divided by the dimensionless volume of the extra dimensions. But in the end, the take-home message is that these actions turn out to be very heavy. So they cannot play the role of the QCD axion or any other axion that might be interesting for fuzzy matter. On the other hand, if you break the shift symmetry at non-perturbative level down to a discrete shift symmetry, here there are two important scenarios. So remember that the actions are part of a complex field where you have theta and tau. Now, if you fix the moduli supersymmetrically, so which means that if you fix both theta and tau by using the same effects as in famous KKT models, what happens is that theta will get a mass of the same order as tau. But as I said earlier, tau has to be larger than 50 TeV to avoid cosmological moduli problems. Hence, also in this case, the actions turn out to be super heavy. On the other hand, if tau, so if the real part of these moduli is fixed by perturbative effects, we know that at this level of approximation, the actions are still flat because they are protected by their shift symmetry, which means that tau now, which is say larger than 50 TeV, would be much larger, I mean its mass would be much larger than the mass of theta developed by instantons. And in this case, similar to his LBS models, so large volume scenarios, in this case, the actions are fixed by non-perturbative effects, the suctions tau are fixed by perturbative effects, so you can create a big hierarchy, and the general expectation is just that the mass of the actions should be exponentially smaller than the mass of the suction. So the suction is larger than 50 TeV or around 50 TeV, and then the actions are, then the mass of the action is exponentially suppressed. Then what is the exact value of the mass of the action depends on the coefficient that you have in the exponent, in the exponential suppression, and that is a feature which is model dependent. So you can go down to 10 to the minus 22 electron volt, 10 to the minus 18, 10 to the minus 10, but that is just a model dependent issue. What is model independent is the fact that they will be, as I said, much lighter than tau. The other interesting issue is that, in general, in these compactifications, you do not have just one modulus, but you have hundreds of them, which means that you are very naturally led to an axios. So many of these axions, which are all very light and have masses which are exponentially suppressed with respect to the mass of tau. Now, the other question is about the axion decay constant. So now maybe I will skip some technical details, but one can quickly look at the canonical normalization for the kinetic terms of the axions, and very easily one can realize that for these close-string axions, depending on the topology of the cycles associated with the axions, they can have a decay constant which is either of order the Kaluza-Klein scale or of order the string scale. So these scales are very large in general, so you expect to be in a regime where these decay constants are not too far from, let's say, the Planck scale or the GUT scale, 10 to the 16, 10 to the 17 GeV, something like this. The only possibility to lower the axion decay constant would be if you lower, as I wrote down here, the string scale. For example, you might go in the intermediate regime, but you need to lower the string scale down to 10 to the 11 GeV. These can correlate with gravitino mass, a gravitino mass around the TeV scale, and also supersymmetric particles around the TeV scale. But in general, you will have some of the moduli which turn out to be too light, lighter than this 50 TeV. So this doesn't seem a very natural limit. And so the take-home message here is that these kind of actions are actually very good for fuzzy vector, because they tend to be very light, ultralight, and they tend to have a very large decay constant. Now, let's quickly go to the other possibility, actions from open strings. In this case, we will find that these are good for the QCD action because they quite naturally give you instead a decay constant, which is in the intermediate scale regime, so something around 10 to the 9, 10 to the 10, or 10 to the 11 GeV, but probably are less interesting for fuzzy dark matter. So in this case, what happens is that, again, you look at this UN gauge theory on a stack of NDT brains, which is anomalous. There is an anomalous U1 there, and you turn on gauge fluxes in these brains. And what happens in general is that the action theta that I was mentioning earlier gets eaten up by these anomalous U1s in the process of anomaly cancellation. And this is nice in a certain sense because then these U1s tend to get a mass of order the string scale, which means that when you look at the effective field theory at energies below the string scale, you see this U1 symmetry, but you don't see the corresponding gauge boson. So it looks like a global symmetry that fits perfectly with the U1 Pechequin picture. And in that case, the action, so the closed string action will be eaten up, and the remaining open string action could play the role of the standard QCD action. Because in that case, you see that you generate a potential, in supersymmetry, this is a deterrent potential, that looks very much like the Higgs potential, where ρ is the radial part of open string field phi, whose phase, e to the I theta, now plays the role of the action. And then there is a constant psi, which is actually, which is more precisely a field-dependent Fourier-Laplace term. And then you see that when you minimize this potential, then the radial part of this phi cancels this psi, this Fourier-Laplace term, that breaks the U1 Pechequin symmetry and sets the decay constant, these open actions. And okay, then from the Chern-Simons action, I will skip again the details. One can find what is the form of the mass of these U1s. So this is the mass coming, as you can see here, from eating up a closed string action, A. So this is the guy that I was calling theta before. Now I'm calling it A because I'm looking at the canonically normalized field. But the important thing is that the mass of this U1 is given by the U1 charge, the gauge coupling with this U1 times the action decay constant squared, where this is the decay constant of the closed string mode. Now, as I said, one should actually check which action survives in the low energy effective field theory, because you always have two actions, so an open string action and a closed string action, where maybe let me go back to this cartoon just to be more precise. So we are in a situation like this, where we have this stack of brains wrapping an internal cycle. Now, the closed string action is associated to the volume of this internal cycle wrapped by these stacks of the 7 brains, whereas the open string action is associated to open strings, which live here on these stacks, on this stack of brains, and you have these open strings which play the role of matter fields, and which can be written as a radial part and the phase will be the open string action. So you have these two actions, and then you have to check which one survives in the low energy effective field theory. So you have to understand which combination of closed and open string action is eaten up by the anomalous U1. And this can be easily checked by looking at the formula for the mass of this anomalous U1 that goes like FA open squared plus FA closed squared. The nice thing is that from string theory, you can compute these FA open and FA closed, and so you can check which one gives you the largest contribution to the mass, and then you can understand which is the mode that gets eaten up. So I mean, if FA open is larger than FA closed, it means that it is the open string action that gets eaten up, and vice versa. Now you can check that when these D7 branes wrap cycles in the bulk, like in the example of the 7 branes that I mentioned earlier, then FA open is larger than FA closed, and it is the open string action that gets eaten up. And so the discussion that I presented earlier about the properties of the closed string actions would hold, because it would tell me that these closed string actions indeed survive in the low energy practical theory, do not get eaten up by any anomalous U1, are ultra light, and have a very large decay constant. So they're perfect for fuzzy dark matter, up to what Veronica will tell you. Good. On the other hand, when you look at local cycles, which, let me go back to this cartoon, local cycles means that we are looking at these branes at singularities. So we are not looking at branes wrapping an internal cycle, but branes at singularities. In that case, FA open turns out to be much smaller than FA closed. And it's interesting that in that case, FA open, if you do the computation, so here I wrote down all these details so that people can go and check if they want. FA open squared, in this case, goes like the string scale squared times tau local, where tau local, let me go back, tau local would be the volume of the cycle which resolves the singularity. So in practice, if you are exactly at the singularity, this tau local will be 0. Actually, when you do the computation, it will not be 0, but it's going to be something very small. So this means that in this case, the decay constant of open string actions would be much smaller than the string scale. So you would very naturally go to a regime where these can be intermediate scale, 10 to 11 GeV, that could be good for reproducing the QCDMs. So this is my last slide. Let me summarize what I said. So in 4-dimensional models coming from string theory, one can get closed string actions and open string actions. So closed string actions come from the dimensional reduction of antisymmetric forms, and very naturally they are ultralight and give rise to large decay constants around 10 to 16 and 10 to 17 GeV, which can be good for fuzzy dark matter, inflation, quintessence, and applications to cosmology and phenomenology of this kind. Open string actions instead arise as the phase of matter fields and have a decay constant which can very easily be in the intermediate regime, 10 to the 10 to 11 GeV. This can be good to get the QCD action, or also to match all these astrophysical hints that point towards this region for the decay constant. As I said, one has to be careful because many actions can be removed from the spectrum by oriented for projection, can be eaten up by anomalous U1s, or they can become too heavy if they are fixed supersymmetrically, which means that if they get the same mass as the suction, given that the suction has to be larger than 50 TeV to avoid cosmological problems, also actions can be too heavy to be good for phenomenological applications. And in order to understand what is their mass, one has to look at modular stabilization. using and keeping in mind the fact that actions enjoy a shift symmetry. So as I said, they can be heavy, which means heavier than 50 TeV if the suctions are fixed perturbatively, but if the suctions are fixed by using perturbative effects, the actions will be exponentially lighter than the suctions, and so they could very easily reach regions where they are of order 10 to minus 22 electron volt, for example, which is good for fuzzy dark matter. And on top of that, from string theory, in general, you get a plethora of these actions, giving rise to an axioms. Let me mention also that a nice prediction that is quite generic and unavoidable in most of the models is that these heavy suctions, when they decay, they always have a non-zero branching ratio into the light actions. So you also produce them via the decay of heavier particles. In this case, they would be relativistic, and they always contribute a bit to axionic dark radiation. So as I said, there are several applications to see the axion, dark radiation, astrophysics, inflation, and quintessence. But I think the nice application is to fuzzy dark matter. And now using the things which I try to review in the simplest possible way now, Veronica will try to answer the question how natural it is from string theory to get exactly the right mass and decay constant that you need to get 100% of fuzzy dark matter. Okay, thank you.
Thanks, Michele. That was a really great overview and very interesting. So I thought, like, I'll ask you a couple of questions now, like specifically about your talk, and then Veronica can do her talk, and then we'll all discuss that. So I wrote down a few questions here. I'll just think of where I can start. So okay, you talked about the open string axions having large decay constant.
The closed strings.
Yes, sorry, I always say that the wrong way around because I think of open as being like an O, and I know I mean closed, and I always say open. Okay, yeah, the closed string axions have this this large decay constant, and in the effective field theory, then how did you say this? We always have we have to have the symmetry. We have to have F larger than Hubble inflation, so that you don't have because you don't want to be like the KK scale to be below the inflationary scale. Like, what would happen? I mean, what would happen if that was the case? Like the world is not 10-dimensional after inflation. Would this just be like a disaster phenomenologically? There's no way we can talk about it, or?
You mean if the inflationary scale is higher than the Kluter-Klein scale?
Yes.
That's a possibility. There is nothing wrong with that. The problem would only be for us a problem of control over the computation. Over the computations which we are doing, and it is just control over the effective field theory, because you have many corrections to the effective field theory which would be there by the fact that you have to include the whole tower of KK modes.
And if that happened,
sorry, so just to finish. So in a certain sense, so at the beginning I said that. So you could have FA, which is larger or smaller than the Hubble scale, and also FA set the scale where the Yuan-Pechik-Queen symmetry is continuously broken. So in a certain sense, when you focus on open string actions, given that they have FA which is much smaller than the KK scale, then you can see this picture. But when you focus on closed string actions, where FA is the string scale or the Kaluza-Klein scale, once you go below the Kaluza-Klein scale to see a four-dimensional effective theory, you are always in a regime where the Peccei-Quinn symmetry is broken spontaneously. And if you want to have things under control, the Hubble scale and inflation should be below that scale.
Okay, yeah, because it was something I thought of like a few times. Like, what would in the case where we've got a global U1 symmetry, and you have it broken after inflation, you get strings, right? You get topological defect strings from the breaking of that symmetry from the Kibble mechanism. And like, yeah, if you were breaking, if compactification was happening after inflation, would you have like some weird topological defects? But yeah, okay, maybe that can't be computed. Now, what other questions should I write down? Okay, so you talked about these different ways of doing moduli stabilization, about KKLT and LVS, and you said that in KKLT the axions and the moduli are fixed, both by non-perturbative physics, and because that's in symmetric between both of them, they get the same masses and the axions are heavy. But in LVS, you fix the moduli perturbatively and the axions non-perturbatively, and thus you can have the hierarchy of scales. And you also mentioned the case that actually the axions could get masses perturbatively as well. So my question is, what determines, physically which one of those scenarios you're in? Like, what is it that's arranged differently that determines whether you get a perturbative mass, a supersymmetric mass, or a mass that breaks supersymmetry?
Yeah, that's a very good question. And so the answer is mainly, so the answer in this case is related to these background fluxes, which you turn on in the extra dimensions. So these are the guys which are responsible for breaking supersymmetry. And in the end, you need to look at the vacuum expectation values of these fluxes. And in particular, the vacuum expectation value of the superpotential, which is generated by these fluxes. And this is something that from the string theory landscape point of view, so you can make a statistical study, right? So you have different string vacua, and for each of them, you have a different value for this quantity, which is called W0. Now, the interesting thing is that it is this quantity which measures the different strength or the relative strength between perturbative and non-perturbative contributions to the scalar potential. So so you can make a scan in the string landscape with different vacuum, and then you can check how many of them will have ultralight axions, and how many of them will have instead heavy axions as in KKLT. And the nice thing is that very generically, this W0 is such that perturbative effects are more important than non-perturbative ones, as you would expect, right? Perturbative physics should be more important than non-perturbative effects. So probably people didn't do this statistical analysis in detail, and this would be a very interesting question. But I think you would find that in most of the landscape, ultralight actions will pop out.
Okay, but you said this W not controls how strong perturbative versus non-perturbative effects are. But what controls whether or not they're more important for axions compared to moduli? Because you can have, as you said, axions get a perturbative mass. You can have them both get non-perturbative masses, or you can have this case where perturbative is more important for moduli, but non-perturbative for axions. So what makes the distinction between the two?
Right. So as I said, this W0 controls the ratio between, if you want, the perturbative contribution to the suction mass and the non-perturbative contribution to the suction mass.
Okay.
So if, let's say, natural value of this W0 will be 1. Because it comes from this flux quanta, from the Dirac quantization condition, which are order 1 numbers. So if this thing is 1, it means that the perturbative contribution to the suction mass is always larger than the non-perturbative one. Then you know that the non-perturbative one is always of the same order as the mass of the axion. So that you know that you are in a regime where the axions are much lighter than the suctions. This is the only model independent and generic statement that you can make. Then if you want to ask the question, how big is this exponential suppression? That is more model dependent because it depends on the rank of the instanton or the number of, or the rank of the gauge group which undergoes these non-perturbative effects and things like this.
Okay, and then like a last question about that. So in the landscape, you're moving around and there's different values of W naught. Can I think of that as like, well, okay, two parts to the question. The first one is like, what sets the value of W naught, and then I would think, can I think of W naught? You said it's associated to fluxes. Can I think of it as like, okay, like in cosmology, we can have magnetic fields. We can have cosmological magnetic fields, and something creates those. So there's some model of magnetogenesis, and that might mean that in ordinary 4D cosmology, you know, somewhere in the inflationary landscape, I get a big load of cosmic magnetic fields, you know, in this Hubble patch, because magnetogenesis happened in one way, and then in some other Hubble patch, I have no magnetic fields. Is the value of W naught ultimately something that's like made dynamically, like something there's, you know, W naught magnetogenesis or something? What selects? Where does that come from?
Right. This is okay. So this is a very good question because let's say what set the value of W naught is, as I said earlier, is the value of these background fluxes. So you have these, is the same thing as for standard electromagnetic fluxes, where you have the Dirac quantization conditions for monopoles, right? And so here you have just a generalization of that. And so these flux quanta are just numbers and discrete numbers. And then this superpotential, this W naught, is just a polynomial function of these fluxes. So it's something that you expect to be of order 110. So that is fixed of that order of magnitude. Then, and when it has got values of order 110, you get ultralight axions. To get axions which are heavy, you need to tune via cancellations in this polynomial. You need to tune this W naught down to exponentially small values. So that's why it is very unnatural to have heavy axions. Okay. First answer. The second answer is that the way we understand now the flux landscape, we just choose by hand this flux quanta. And actually different choices of these flux quanta give rise to the different vacua we see in the landscape. And at the moment, we are not aware of a dynamical mechanism to generate these background values. But given that, as I said earlier, in string theory, there should be no parameter, which is free. So you should see also these flux quanta as arising from a dynamical Higgs-like mechanism. But I think that in order to understand that, one needs a proper understanding of string field theory. So of M theory or a complete non-perturbative formulation of the theory, which we do not have.
Okay. I could go on with questions for ages and ages, but I think we'll move on to Veronica's talk, and then we can keep on talking about everything.
Yeah, thank you for the questions.
Yeah, thanks. So I think if you stop sharing, and then Veronica can start.
Okay. I hope this is working. Is it working or not?
I can see your browser.
And now, are you seeing something?
Yes, now I see your.
Very well. Very well. Okay, so first of all, thank you, David. And I want also to thank all the other organizers for the opportunity to give this talk and for organizing such a nice workshop. So I'm going to talk about fuzzy dark matter from strings. And this talk is based on a work made in collaboration with Michele, Alexander Westphal, and Arthur Habecker. I know that fuzzy dark matter doesn't need a presentation in this workshop, but let me warm up with explaining just a few things about fuzzy dark matter. So fuzzy dark matter should be a form of dark matter which is made out of ultralight particles, and in one of its prominent versions is actually made out of axions whose mass should be around 10 to the minus 22 electron volt, and they should also have a high decay constant around 10 to the 16, 10 to the 17 GeV. The nice thing about fuzzy dark matter is that these axions are usually produced by misalignment angle, and so they're naturally cooled, and they can develop solitonic structure that, through Bose-Einstein condensate, and this kind of dark matter can then solve the core cost problem and also other problems like the missing satellite problem, so reduce the abundance of low mass Hellas. I've been quite quick. So why should we look in string theory? Well, IDK constants are usually related to energy theory, and we know that, as Michele already said, string theory is a UV complete theory. And in particular, I saw that some authors actually, said that the nature of fuzzy dark matter can be a little bit more varied. And so maybe it cannot be made out of a single axion like particle, but maybe few of them still having extremely light mass and high decay constant. And as Michele just said, we know that there is this axivus, which is predicted by string theory. At tree level, they appear as massless fields, and they can be, in order to be light, they need, and in general, they are stabilized using non-perturbative corrections. So for instance, you can use ED3 brane instantons or Gugino condensations. The convention I'm going to use in this talk is the following. So we're just going to consider plain Lagrangian with where here F is the axion, decay constant. A is just a factor of order 1 at this level. S will be an instanton action. And since we want to deal with physical quantity, maybe it is better to introduce the canonically normalized field theta. And so what we want to do is we want to find a model where dark matter is made out of only, at this stage, only one single axion, which satisfies the right mass and decay constant, through the misalignment mechanism. So the relative abundance of dark matter will be given by this form here, where theta mi is the misalignment angle. And okay, from the Lagrangian, we can also say that the physical mass for the axion field is given by this formula here. Just by looking at these, let's say, quite naive quantities, we can already say something interesting, which is the following. If we require that the mass, if we require to match the right mass and the right decay constant, given that the axion mass has this shape here, and we just naively assume that the prefactor A here has to be of order 1, what we understand is that S times F, so the instanton action times the decay constant of the axion, should be slightly, or let's say of order n Planck, or slightly larger. But this is actually against the weak gravity conjecture for axions, at least in its strong statement. And despite the fact that the weak gravity conjecture is still a conjecture because it has not been proved, actually it is based on concrete examples. And in general, it is not that easy to evade it, as we will see in a minute. So as Michele said, our best candidate in order to be fuzzy dark matter are closed string axions. So since we knew that we wanted to match this kind of condition, we first briefly scanned the various possibilities in terms of closed string axions. In type 2b, we have 4 kinds of axions, C0, C2, B2, and C4, which are integrations of antisymmetric forms over cycles, okay? And let's say the simple scan we made gave these results. In particular, here I have to say that this GS is the string coupling, so it has to be much more than 1. So we see that in general, for these 3 kinds of axions, more or less, I mean, we can get S times F for order mass Planck, but of course, we wanted to get the best case scenario, right? So we studied a little bit more the C4 axions. C4 axions are the imaginary parts of Kähler moduli. And Kähler moduli are related to the size of the Calabi-Yau in general and of 4 cycles. So we decided to study 2 kinds of geometries. I mean, it will be clear in a moment that the best candidates for being fuzzy dark matters are the closed string axions related to the overall volume. So we restricted our study to 2 simple setups. In the first case, we have that the overall volume of the extra dimensions is parameterized by a single field. In the other case, it is parameterized by 2 different fields. And I mean, a pictorial view of this thing, you probably, okay, is this one. So in one case, you have that the overall volume is just proportional to a single field. In this other case, it is proportional to 2 fields. That pictorially here are the 2 areas. For these kinds of axions, the shape of the mass is this one in general. And here we have that curly V is the volume of the extra dimensions, while, okay, GS is still the string coupling. AI is the prefactor, which appears in front of the non-perturbative corrections to the superpotential. And W0 is, as Michele already said, the 3-level superpotential. So we tried to force fuzzy dark matter into this model, and it will be clear in a moment why I'm saying force. And these are the results that we got. So in the first case, we got a relatively small volume in string units, but we had, in order to get the right mass, we have to tune these 3 guys enormously. And in particular, as Michele already said, at this level, you can treat them as constants, but actually they are not constants. They depend on the vacuum expectation value of several fields. And if you have to tune them too much, actually you cannot say that your effective field theory is under control anymore. Here you see 2 kinds of values. In the first case, we are trying to match 10 to the minus 22 electron volt for the mass. And in this other case, we're trying to match 10 to the minus 21. And you see that just 1 order of magnitude implies a huge difference in terms of fine tuning. In the other case, you have an additional degree of freedom, so you can also tune the overall volume. But in order to mild the tuning on these 3 parameters, you actually have to tune it extremely large. And actually, the overall volume of extra dimension is not only a number, but it also tells you what is the hierarchy between energy scales. And in particular, such a huge volume for the extra dimensions actually implies TeV string scale, which may have a lot of phenomenological problem, and anyway would be, an extremely restrictive bound for model building. Another thing that has to be noticed is that in order to match the right scale, another thing which is slightly unnatural is that in order to have such a huge volume for the extra dimensions, but still having an axion who has the right mass, you need to stabilize the overall volume in an extremely anisotropic way. So this volume has to be stretched a lot. And there are examples where this can be done, but of course this would not be the most natural case in general. So why is it so difficult to reproduce fuzzy dark matter in this context? Because it doesn't seem to be so difficult. Well, I can explain it, or I can try to explain it in three lines. So here we are considering large cycles. For large cycles, you have that this is the condition or the relation between the decay constant and the instanton action. And let's rewrite down the mass, just summing up W naught, GS, and the prefactor in one single factor here. We have always assumed standard values for the misalignment angles, so small values in general. And let's say that in the first case, you want to have 100% of fuzzy dark matter, and assuming that you can match the right mass for the axion. This is just a simple equation coming from the dark matter abundance equation, and you see that your instanton action needs to be of order 60 or something like that. On the other hand, if you just try to find the right mass, assuming an order 1 coefficient here, this would require an instanton action, which is far larger. And so there is this tension between finding 100% of dark matter and matching the right mass. And in particular, in the first case I showed you, you have just a single degree of freedom for the volume. And in particular, this implies that there is a relation between the volume of the extra dimension and your instanton action. So the only thing that you can fine tune in order to mild this tension is tuning A, but then you find that your effective filter is not under control anymore. In the other case, you have an additional degree of freedom. So there is not a relation between the extra dimension volume and instanton action. So you can fine tune V, but then you end up with an isotropic compactification and a type string scale. Another thing that I want to say is that actually there can be, there is a good candidate, or there are good candidates, good, let's say, fuzzy dark matter candidates to represent 100% of dark matter, but they are slightly heavier. So they are 3 orders of magnitude heavier with respect to the standard mass that one would require in order to match the fuzzy dark matter model, 10 to the minus 19, also a little bit larger, but that is the order of magnitude, let's say. Another thing that I want to mention is that in case you want to deal with more than one fuzzy dark matter particle, the most natural thing would be that heavier axions will represent larger percentages of dark matter. The vice versa is very, very, very unlikely. And so this is the only way that thing may go, especially when we are talking about closed string axions. And especially because, this kind of relation is quite generic for large volumes, or for axions coming from overall volumes, so large cycles in general. So this is the situation about closed axions. What is the situation about open string axions? Because Michele said that they tend to have decay constants which are, let's say, much smaller, but let's try to construct something here as well. So as we already, Michele already told us that actually having open string axions requires a little bit more structure than open string axions, which are mainly related just to topology. Here we need a shrinkable cycle, so a Kähler modulus which shrinks to 0. We need to have a brane setup to turn on non-zero Wald volume gauge fluxes, and in general, after anomaly cancellation, you get that through Stuckelberg mechanism, this axion is eaten up, and in principle, after supersymmetry breaking, you can develop a sort of Mexican hat potential for the radial part of this C field. Then you are left with a flat direction, which is the phase field there. And that is actually the Nambu-Goldstone boson of your Hitchhiking mechanism. And what are the features that may characterize this kind of axions? Well, this kind of axions usually have a decay constant which scales like inverse powers of the overall volume. And they can get a mass through hidden sector strong dynamics, or in particular, the form of their mass will be this one, and the QCD scale of the hidden sector will scale like this, where C is fixed by one loop beta function, and G is GS actually, so it is related to the dilaton vacuum expectation value. Now, since we want to have a decay constant as high as possible, we're going to consider here the case where P is equal 1, so that the decay constant is not too much suppressed. And we impose 100% of fuzzy dark matter and with the right mass. And what we end up with is that the volume, again, is extremely small. The strong scale of the hidden sector is extremely small as well, but we're still, I mean, looking at the stabilization of S, we're still in the perturbative regime in this setup. The main problem related to this setup is that usually you cannot get, you not use this kind of method in order to get ultralight axions. The setup is quite less general than before. And in particular, you have to be careful in assuming that your fuzzy dark matter must represent 100% of dark matter, because here you tend to create blue balls. And so you may have an additional contribution to dark matter. And so, I mean, these kinds of model needs, I mean, one should compute things properly, but of course you need a specific model. I just wanted to stress a little bit problems that can arise in this context. The last thing that I want to mention is this one. At a certain point, we decide, we realize that, okay, here we need too much fine tuning everywhere. Can we then account for large misalignment angles? So here we assume this kind of relation between a decay constant and the Hubble parameter, which is, by the way, quite natural, because anyway, these decay constants are extremely high. And in this context, the only thing that changes in the dark matter abundance is that you have an additional factor, F, which is the form factor, that has to be estimated to have this form. Here I take A equals 7/6. There are other values that can be taken. These values actually depend on how the axion mass scales with the temperature at temperatures higher than lambda, so the strong, the QCD scale or the instanton scale. But let's fix this value like this. And well, we found that in order to avoid any other fine tuning, we need to tune the misalignment angle extremely near to pi. And then one would ask, okay, but if you start too near to the maximum, then you can end up having domain wall problems and other problems. Then we try to figure out which were the consequences in taking such a huge value. I mean, in order to avoid the domain wall problem, you need to impose that the quantum fluctuation of your axion field are much less than the initial displacement from the maximum. So just imposing this relation, you end up with an upper bound on H. And you may think that it is quite restrictive, but actually we found out that just from isocurvature perturbations bound, you get a more restrictive bound. Then, of course, I mean, maybe you do not have any kinds of problem with domain walls, but in principle, anyway, you should be able to explain why such a value has to be chosen in order to reproduce your fuzzy dark matter model in this context. So my conclusions are the following. Yes, string theory predicts the plenitude of a plethora of axion-like particles, and this is quite a generic feature. But anyway, it is not that easy to have 100% dark matter in just a single ultralight axions. In particular, if you want to match those values which are required from the fuzzy dark matter model. So 10 to the minus 22 electron volt is really a hard task for string theory. And why is it not that easy? It is not that easy because it is not that easy to overcome the weak gravity conjecture for axions. It is not easy because, I mean, you need to justify a little bit why you choose a certain fine tuning. And I mean, if you have to fine tune the overall volume, then you have a tough string scale. Otherwise, you need to tune all the other parameters, but then you tend to have an effective field theory which is not under control. Or you can tune the misalignment angle, but you should be able to justify it in some way, also maybe from a statistical point of view. And also with open string axion, maybe, of course, they are not the best candidates. And in particular, the setup in which you can have them is not that general. And in particular, in assuming that you have an open string axion as fuzzy dark matter, you need also to pay attention to glue balls in general, glue balls productions and other effects which can contribute to dark matter. So I think that if fuzzy dark matter is detected, that would be a real challenge for string theory. Thank you.
Great.
Thank you.
Thanks, Veronica. That's a really interesting talk, and I have a lot of questions. So, so I'll start. One of the key problems here seemed to be, the strong form of the weak gravity conjecture, that you needed SF larger than M Planck to really get the fuzzy dark matter relic abundance right. Does that mean? And you said you always get lighter axions contributing less of the dark matter. Mm-hmm. Does that mean that, like, the weak gravity conjecture, is it kind of protecting you from overclosing the universe in a way? Does it mean that if you fix the decay constant to always be, the KK scale and it's some large scale 10 to the 16 GeV, Michele was saying, is the weak gravity conjecture saving you from overclosing the universe?
Another way for interpreting it, but in general, actually there is the mild version of the weak gravity conjecture which actually allows you to have particles which actually satisfy or may have S times F, which is larger than M Planck. The main point is that it is really, in principle you can have it, but it is extremely hard to find them. So I do not really know whether, and I do not know whether to interpret this conjecture. Maybe it can be another way to interpret the conjecture. For sure, it prevents overclosure of the universe, but I do not really know if you can really interpret it this way. Let me think a little bit.
It seems to be like for the fuzzy case, for the axions lighter than maybe it would only be for axions lighter than a certain value, I suppose. So you said you get the relic abundance just right at 10 to the minus 19 EV.
Yeah.
So it's kind of saving you from overclosing the universe for all of the lighter guys.
Yeah, maybe yes, probably yes. Indeed, it can be indeed. For instance, the natural percentage of dark matter that you can get at 10 to the minus 22 electron volt is actually a few percent. And I suppose that if you go down in mass, you get smaller and smaller percentages. So in some sense, maybe yes. I haven't think about. I did not realize it, but it can be. For sure, it can be. You cannot get at least, for example, because for closed string axions, you may be right, because in that case you have let's say you can see just from the geometrical point of view that there is this strong relation between instanton action and decay constant. So I would say yes, but that applies only for closed string axions. For open string axions, actually, you have a little bit more freedom to overclose the universe as much as you want.
So while we're on that topic, I have two other topics I want to ask you about. But while you're on that topic, do you mind if I just share my screen for a minute and show you a plot?
Should I stop sharing mine?
Yeah, if you stop sharing yours, I'd just like to kind of.
Okay, very well. Now I.
And then we'll come back to something else, right? So the topic of this workshop is fuzzy dark matter being, all of the dark matter. But a subject that's close to my heart is the presence of these low mass subdominant cases. and also what I call the 1 Hertz axion window. So I just want to share a plot about this. I'm just finding it. Okay, I've got my figures here. I'll share my screen. This. Okay, so I want to show this plot. So this is from this is kind of collecting all the different bounds on fuzzy-like axions, and I use it as a bit of propaganda sometimes. So here's all the mass ranges. Here's the allowed cosmic density. And as we know, fuzzy dark matter sits in this 10 to the minus 22, 10 to the minus 20 EV mass range. It's probed by the Lyman alpha forest. And Lyman alpha forest, we think, also overlaps with these bounds from Eridanus 2 due to the survival of the old star cluster. And there are ways around that, and we'll probably hear about them from Siyu Shui later in the workshop, where you can survive at 10 to the minus 22. Anyway, this region is under pressure astrophysically if you're all the dark matter, and your preferred mass, if you saturate the weak gravity conjecture, I think would be 10 to the minus 19 EV, which is on the boundary between Eridanus 2 and black hole superradiance. So what I want to ask is, what about these lighter guys? So I've drawn here a predicted region of dark matter abundance. If I fix the mass to be a constant, I fix FA to be the gut scale plus or minus an order of magnitude, and theta equals 1. And that makes some prediction. And you said, okay, fuzzy dark matter might be 1% of the dark matter on my plot. That's kind of here. And we can try and probe that with, more advanced Lyman alpha forest. Here I'm showing the intensity mapping with SKA. So is there, I'll be quick, is there a natural region in axion mass versus density predicted from string theory? If you give up the requirement that you're all the dark matter, can you draw a region like my, naive gut scale region on this plot? And it's nice because it, we will have these improved, say intensity mapping surveys I'm showing here in purple, or next generation CMB, or improved Lyman alpha, or pulsar timing arrays. And if we can really start to actually test the predictions of string theory, so you said, you don't expect fuzzy dark matter is all the dark matter, but what's the subdominant prediction?
Yes, of course you can plot exactly the same thing starting from 10 to minus 19, which is the most, in that case you would saturate the dark matter abundance, but of course, yes, we can, yes, for sure, we can reproduce the same plot, and maybe it also follows the 2 dashed black lines, by the way. Let me see.
But I agree that one could, you can take a value for the initial misalignment angle, which is not tuned, and then you would get here a line in this plot that would be the natural prediction from string theory for different masses and different abundances of dark matter.
Yes, of course, you can just have a little bit, we have a little bit of freedom in model building, so maybe we can also get an area instead of a line. But
yeah, I agree.
Probably not as large as yours.
Yeah, right, because, you said there's this A parameter, right, but you don't want to tune too much. So if you allowed them all, a little bit of variation, there would be some region in this plot, and it might be a bit more motivated than just my kind of rough gut scale FA thing here. So I'd be very interested to.
Yeah, but the nice thing is that all these parameters that we were tuning, they were in front of exponentials, so we had to tune like crazy. But actually, in the end, what matters is the coefficient in the exponent, right? Because you have the exponential sensitivity, and that is something that it is fixed for us. So I think we can get something quite precise with this prediction.
Yeah, definitely.
So, for example, Veronica, you know this because so when you set the mass, which is exact, so you said that when you set the mass, which is 10 to the 19 GeV,
yeah,
then without tuning anything, you get 100% of that matter.
Yeah.
But now, if you do not tune anything, and the mass is 10 to the minus 22 electron volt, then you get
few percentage of dark matter, 5-8% of dark matter.
5-8%. Okay, I didn't remember this. That's interesting, also.
Yeah, so that would be, you know, on my plot just there, that would be something that we could test with intensity mapping or with next generation Lyman alpha. So it would be nice to have what, you know, this kind of you know, some kind of region like this for a target for experiments.
By the beginning of the work.
That's what I keep on telling people, you know, is that there's a target kind of being given to us also from high energy theory of subdominant light particles, because there should be lots of them, right? And yeah, and it's nice that they're predicted to be subdominant if we don't have an overclosure problem for these light particles,
right?
But we also have tools to look for them,
right?
So I have a couple more questions. Moving on from that, let me remind myself what they were. I had two. Okay. So you talked about the tuning of the misalignment angle.
Yeah.
So you were allowing yourself there to tune to values close to pi. Is that right?
Yeah.
Right.
Yes.
So there's an interesting way around that Siyu Xue might tell us about in his talk, to do with this tuning called the extreme, what that they call the extreme axion.
Okay.
And as you showed, right, in the case where you tune the misalignment angle, you can lower the decay constant. And in your case, is that what's allowing you to not butt up against the weak gravity conjecture? You tune the misalignment angle close to pi, and you lower the decay constant.
Yeah.
Right. So that's another interesting one phenomenologically.
Sorry, David. So the decay constant remains 10 to the 17 GeV.
Yes, but it's the same effect.
Yeah, it's the same effect that the mass can be 10 to the minus 22 electron volt without the need to tune anything else except for this initial misalignment angle so that you're close to the maximum.
Could you at the same time then reduce F?
F is fixed. F.
No, but you could reduce F. Yes.
In which way?
You just increase the volumes of your cycles. You would reduce the mass also.
Yes, you can, just because of course it won't affect that much the mass, but it will affect. No, it would affect too much.
It would affect the mass a lot because it's exponentially sensitive.
Yes, it would affect the mass too much, and then actually a small effect will spoil your mass prediction. So actually that cannot be done, in my personal opinion.
Okay, because there's a phenomenologically interesting model there where you keep the mass at 10 to the minus 22, but you lower F to about 10 to the 15 GeV, maybe 10 to the 14.
Okay.
And that gets around the bounds from the Lyman alpha forest, because when you tune the initial misalignment angle onto the top, then the perturbations have a tachyonic instability, and this boosts the power such that you can match the Lyman alpha forest. And it would be interesting if that was something that was consistent with weak gravity, but you're saying that would be even harder because you'd want to keep the mass at 10 to the minus 22, but you lower F, and that means that you've got to do some other tuning, or...
Yeah, because I think that in that case, they were people are considering F and M as independent.
Yes.
And the problem is that for us, they are related by the underlying construction.
And in particular, you end up with having e to the, I mean, your mass scales like e to the minus 1/2f.
Yeah.
So you're ruined. If you change something there, you're ruined. Your mass becomes something completely different.
Right. Yeah. Okay. So the mask is.
But the other interesting thing that we noticed was that even if you tune close to the maximum, then I mean the fluctuations during inflation do not generate domain walls. So you do not just go on the other minimum.
Right.
Once you satisfy the bound from isocurvature perturbations, then you're safe.
Okay. Aha, and by the way, reducing F, as you said, but tuning the misalignment angle probably also lowers a little bit the constraints on isocurvature becomes milder, by the way. So yes, if it could be possible, I would have done it, but it is not.
Okay. I have one more kind of specific question about the, let me say it the right way around, but the open string axions. Okay. I always want to say closed for them. Okay, open string axions. So this model that you talked about there with a hidden sector, a strongly coupled hidden sector. As you probably came across in the literature, this was something talked about purely from a 4D perspective by Davudassil,
Okay.
as a model for Davudassil and, oh God, I've forgotten the name of the other author. Chris, I think is his first name. Anyway, Human Davudassil and Chris, someone. Sorry, for forgetting your name if you're watching this. But I spoke to him about it. Okay, but in that case where you've got a like a kind of a more concrete model for the particle physics content, is it possible in those models, or actually in closed string or open string models, to say anything about the coupling of FDM to the standard model?
I'm thinking about U1 gauge mixing or something like that, but I want Michele to say it because I'm not an expert and I know he's probably much better than me. Something like that. No, Michele?
I think, yeah, the only way is to use kinetic mixing.
So because you're in these completely different parts of the manifold, you don't talk to the standard model at all.
No. I mean, so these will be two different. So you will have the standard model on a stack of branes. Then there will be another stack of branes which is geometrically separated in the x dimensions. This is your hidden sector where you have the strong dynamics and positive dark matter. And then actually you will have some kind of loops between the two that generate a kinetic mixing between U1s. I think this would be the way to generate the coupling with the standard model.
But
then the feeding, sorry.
It works also with strong dynamics, so SUN or something like that. Because I think that David was talking about SUN.
No, but I agree. But then you will also have some U1s.
Okay.
So you will have SUN and also some U1 factors that will give you some kinetic mixing. But then I guess that the coupling will be very, very small, weaker than Planckian, I guess. Something.
But that would be if I'm thinking of this rightly, it's a kinetic mixing with the photon, and that would give you an axion photon coupling to the standard model. So the searches, the FDM searches on the photon couple, photon coupling constraints at FDM type masses are like not very good, and even like the very nice ideas for searches there's the dance, this storage ring cavity, they don't get down past this like Planckian coupling that you're talking about. But what about a fermion coupling? The d mu a, f gamma mu gamma 5f to some fermion. Is there any way to say anything about those? Because that's where, and I'm bringing this up because I'm going to pair you with the talk with Gary Centers.
Right.
Casper will be able to place constraints on the axion nucleon coupling in this kind of mass range. Or I mean, it's the standard model fermions are on this completely different stack of brains.
Yeah, I mean, at leading order, they would be completely decoupled. I don't know if via some loops you might generate some effective interactions, but they would be extremely small. So my feeling is that, yeah, these couplings would be almost undetectable. I mean, I don't see.
On the front arc matter.
Yeah.
Well, maybe one final question along those lines then. So you've come up now with two different models, Veronica, for fuzzy dark matter. You've got your closed string axions on these 4 cycles, and you've got your open string axions on the like another singularity completely hidden sector. Is there any way to get maybe not a fuzzy dark matter mass, but a light axion from the standard model, from a grand unified gauge group? So I've seen in Bobby Acharya's M theory axiverse paper, Acharya et al. They get an axion with a mass of about 10 to the minus 15 eV, related to I think gut group instantons. Is that something that is it special to like M theory, or is that something that you could get in type 2b? And that one, I think, you might be able to. It's 10 to the minus 15 EV. I still call that kind of fuzzy dark matter. It lives in this nice window that's not constrained by black hole superradiance. And maybe we can say something about its standard model couplings. Is that a model that you've looked at or you've thought of looking at? Axions on the standard model brains.
I haven't thought about this. Well, I would say that. Well, actually, Michele, tell me if I'm wrong, but I'm not expecting something much different from anyway closed or open string axion. Which other string axion should I have in this case? I mean, on the visible sector. Let's say that I put the visible sector somewhere. There I have all my closed string axion, all my open string axion, but any other axions in the theory from, let's say, stack of brains or matter on the stack of brains. Do you have any idea? I've never seen these things, actually.
No, yeah. Yeah, I'm thinking.
So kind of like another, like, so you could get the QCD axion, right? But like another.
Maybe you need to have. You need to have a situation where. It could be maybe a situation where you have 2 stacks of brains which intersect. One is the standard model, and the other is a sector which is not hidden because they intersect, because there is an intersection. But the other cycle, I think, supports a hyper-weak gauge theory, probably, where the gauge coupling is very small. So in that sense, it's hidden, even if all the particles would be charged under that. And maybe this could give rise to strong dynamics at very low scale, and then it could give rise to some very light open string axion, which could be that guy.
Okay, it doesn't seem to come out in quite the same.
Setup. No, it's a different setup.
In quite the same way as it does for M theory.
No, from M theory is different.
Okay.
And actually, these M theory constructions are more an effective theory, string-inspired constructions. Yeah, I think you would need something like two cycles, a big cycle and a small cycle, which intersect, and they are wrapped by branes. And then in the big cycle, you have this hyper-weak gauge theory with axons there that are not completely decoupled because there is still an intersection. So this might work, but I didn't look at this.
You define it at the intersection.
You need the intersection.
No, and you define this matter field in the intersection, or not? Because otherwise I cannot.
No, but the important thing is to have an intersection. Then they will couple somehow.
Okay.
Yeah, it doesn't look like the most natural thing.
Yeah, okay. Okay, so coupulates the standard model hard for fuzzy dark matter.
Yes, I agree. Yes. All
right. Well, I think we'll tie up there. I've questioned you enough, and you've both given really nice talks. And I suppose we can't go around anymore saying that fuzzy dark matter, all the dark matter, is a really natural prediction of string theory. But as you said, Veronica, if there was evidence for it, it would be a challenge. But also, I like this idea that fuzzy dark matter, all the dark matter, not a prediction from string theory, but also under tension from the astrophysical observations. But maybe these that these subdominance axions maybe are a prediction, and they're actually something that isn't excluded and that we can search for. So I'll take that positive spin away from it.
Yeah, I agree.
Great. Okay, well, I'll stop recording now.